All right, everyone, please take your seats and welcome to the first session of the afternoon. So we're going to start with Amir Arkan, who's going to speak about generalized Renyi entropy accumulation and generalized quantum probability estimation. So Amir, please, the floor is yours.
Thank you. This is a joint work with Thomas Hen from Weizmann Institute and Ernest Tan from University of Waterloo, who's also here. Okay, so okay. All right, so let's start with the first part, which is the main results. I'm going to start with introducing a family of entropies that are a generalization to von Neumann entropies. These family are called Renyi entropies, and they can be characterized with one real parameter alpha. In particular, for the purpose of this talk, I'm going to only focus on the conditional Renyi entropies that can be defined through their corresponding divergence as follows that you can see. The exact definition doesn't matter. You'll probably see them in the next presentation. Okay, but to get a sense of what these entropies are, let's look at one particular property of them, which is the monotonicity with respect to any parameter. They're essentially monotonically decreasing with respect to this parameter. For example, if you look at the regime where alpha is bigger than 1, and we specifically looking at the extreme points of alpha 1 and alpha infinity, we recover the usual von Neumann entropy and the min entropy. And you can see that these Renyi entropies are somewhat interpolating between these two extreme cases in this particular region. But why do we care about them? Well, it turns out that they're quite useful in a lot of information theoretic tasks. For example, in the task of quantum decoupling theorem and specialization of it, the private simplification, which characterizes the secret key length from a QKD protocol, also data compression and lots of others. Okay, now moving forward. So if we look at the von Neumann entropies, there is a particular chain rule that is of interest for our purpose. And that is that if we have a n-partite state, and we are interested in calculating its conditional entropy such that we have like n different registers in the left-hand side of the conditioning, we can use this particular chain rule to decompose it into a bunch of other von Neumann entropies, where this time on the left-hand side of the conditioning register, only one register appears, as you can see up here. But a natural question here would be, well, can we generalize this to the Renyi entropies? And the answer to that is, it would be really good, but unfortunately, no. We cannot do this. However, one can ask, can we sort of get something almost close to an equality, some form of inequality? And the answer to which is, well, under if you satisfy some assumptions, then yes, and you need to use the generalized entropy accumulation framework. But what are those assumptions? So essentially, what you need to have is that your final state the final state that you're going to calculate this conditional entropy needs to be generated by applying these sequence of channels. And also the registers that are going to appear on the left-hand side has to be generated sequentially by these channels, where you present them by these A. And these channels could be quite arbitrary as long as they satisfy a particular non-signaling condition such that they cannot signal from the R register to the E register there. So as long as you have these set of assumptions, you can use the result of this framework, which essentially gives you something quite similar to what we were looking for. So you can see that both sides of this inequality is almost similar to what we wanted, except that we have to take the worst case over the input to the each of these channels. Okay, now moving forward, we can ask a more important question again, and that would be, what if we condition on a particular event? And what do I mean by that? Let's say we still have this, again, this sequential structure of the channels, except this time each channels generate an extra output registers, which is a classical register. And we are defining an event based over these registers. And we're asking exactly the same question, except this time we're going to calculate this conditional entropy over a state condition on this particular event? And well, the answer to that, based on the current existing method, is yes, there is a solution to that, and that is just applying generalized entropy accumulation with testing. So it's an extension to what I showed you previously. Okay, but I kept talking about these sequence of channels, but I didn't give you any intuition. So let's see how we can think of it to get some intuition on this. So imagine we are dealing with a n-round protocol, in which case each of these channels can be corresponded to whatever happens at each single round of that particular protocol. For example, we can see it as you can see this as Alice and Bob receiving a qubit and measuring it. So this could be the action of a single round protocol. And then the C register here are somewhat accumulating the test data, and the sense in which they accumulate this can be seen in, for example, in a BB84 protocol, these C registers record whether a round is a test round or not. And if it's a test round, whether the measurement results for Alice and Bob matches. Another example is the CHSH game, where again, these registers record whether we have a test round or not, and if so, whether the game is won or lost. Okay, now going back to the generalized entropy accumulation, let's look at a little bit more detail of what it has to offer for the case where we have conditioning on some event. Let me introduce some notation. So here we have omega, which is an acceptance set on the classical registers. And then we have sigma, which is the set of all possible states that can be generated at each round of the protocol. And then we also define S of omega, the set of all frequency distributions within the acceptance that can be accepted in the protocol. And using the generalized entropy accumulation, we can get the following result for the case where we condition on some particular event. So I want you to point out on a single important property here, and that is the for the first term correction. You can see that we have this f of q function. We refer to this as a min trade-off function, which is essentially an affine function that lower bounds on the worst case von Neumann entropy, conditional entropy. Now, if you look closely, you see that the bound is kind of independent of the choice of like we have an extra degree of freedom on the choice of this min trade-off function. So that means if we want to get the best results, we have to optimize over this min trade-off function, which is quite difficult task to do so. And also, well, the entire bound may not, in fact, be optimal in general. So to resolve these issues, we introduced this new generalized Renyi entropy accumulation framework, which I'm going to explain to you a simplified version of it. So again, we still have the same structure of the channels and same notations and all, except that this time under this framework, what we get is a little bit different for the first term correction. And the first order term here is a double optimization quantity where the objective function is a KL divergence and some linear combination of the Renyi conditional entropy. Now, despite the horrible looking of this thing, it can be reformulated into an equivalent convex optimization, which is quite nice. And also, you can even further simplify this to get a bound, write it down in terms of von Neumann entropy, and yet you get better results compared to the previous generalized entropy accumulation. Okay, now let's move to the proof techniques. So I'm going to introduce something called quantum estimation score system entropy, quite long name for it. This is defined for a classical quantum states where the classical registers in general could appear at both sides of the conditioning system, you can see here. And then, so I will explain to you in a bit what this exactly has to offer. But just for a hint, this superscript of F here, the role that it's going to play is it's going to be some form of estimator on this divergence term that appears in the exponent. So this is going to be some form of estimator. Okay, this is almost the same as the quantum estimation factors that was introduced by Zhang et al. A while back. And also this formulation of looking at it as an entropy-like quantity is based on a recent result of the F-weighted Renyi entropies that is introduced by Van Himbeck et al. Quite recently. Okay, this is horrible. Let's try to understand what this thing is. So let's specialize this. Special case, let's say we have only one classical register and that's only appearing on the conditioning system, in which case we have this really nice, simple formula for these QES entropies. And let us ask ourselves this very important question. Can we develop some nice framework that allows us for each value of C, we lower bounds these score function F, we lower bound the conditional entropy with these score function F of C? In other words, can we have this particular inequality under some framework? So the first attempt would be, well, can we always do this? Can we develop a framework that always satisfies this construction? And it turns out that it's quite difficult and, well, we couldn't do it. As for the second attempt is that, well, now that we cannot do it always, maybe we can just argue it as, on a average sense. So what if these functions on average are a lower bound on the entropy? And it turns out that this is also still hard, quite hard to develop. Now, a little bit wild formula. Let's see what if we can make it for some sort of average. And what do I mean by that? So if we look at the this simplified case, and if we look at the term within the log, this looks like some form of an average because we have like a sum over probabilities, except that we have this extra exponentiation function here that appears. So you can see that if we look hard enough into this, up to taking a log and forgetting about the fact that we're taking the exponentiation, we exponent. We're taking the 2 to the power of this thing. This is some form of a average quantity. So the term that it is being referred to is the log min exponential average. So essentially, this means that a non-negativity of these FQES entropies are corresponding to having these score functions lower bound the conditional entropy. Okay, but why did I went through all these hardship to introduce these things? Because it turns out that these QES entropies also satisfy some form of entropy accumulation. Again, same structure, sequential of the channels, except now you can see that I dropped the second register that passed through along these channels, and that's only for the simplicity. Let us define the full estimator, f of full, such that it's just the sum over all these single round estimators. And in which case, we showed that these QES entropies are satisfying a form of entropy accumulation, in the sense that you can accumulate QES entropies of the single round to get a bound on the QES entropy for the full round, n round of the protocol. Another way to look at this, to sort of interpret this result, is that essentially it tells us that we can accumulate single round estimators into the full estimator to estimate the final entropy, which was the whole goal in the first place. Okay. All right, so this is quite similar to the Zhang et al. Work, where they used almost the same technique, except under the model of the original entropy accumulation, to develop this QEF entropy accumulation as well. Whereas for our case, we proved it under the more general framework, which is generalized entropy accumulation. I should also point out that there's another work by Van Hembeek et al. Quite recently that obtains analogous results, and except that it's under a little bit different model than what we have here. Okay, now let's look at some further simplification of this. Now, the Zhang et al. Showed that after conditioning the state on some event, the entropy is bounded by the worst case value of the full estimator condition on that particular event. But this is not easy actually resolved because it still has some complication in the sense that you still have the degree of freedom of choosing the best QES. And then this is the same hardness as to picking up the best min trade-off function in the entropy accumulation. So what we did, we showed that the maximization over the choice of these estimators can be formulated as a dual to a convex optimization, which after you solving this, you get the results that I showed you a little bit earlier. Okay, and here's a plot of the power of our technique. The purple one is what you would get from ours, and the red one is what you can get from the best known technique. This is for the qubit BB84 without any loss. And you can see it's quite a significant improvement. Okay, now the bound that we get on these Renyi conditional entropies are suitable for fixed length protocols, those that make an accept and abort decision and based on a condition on accept and getting an accept, generate a fixed length key. And the bound that we get, I should also point out, that are nearly tight up to typicality. And also, based on this recent result, the bound that we get on the QES entropies can also yield security proof for the variable length protocols, which are the one that you can adjust the length of the key based on the statistics that you get throughout the protocol. And then with this result, our finding allows a full adaptive version of these protocols inspired by the work of the quantum probability estimation. Okay, now to summarize, so we introduced full Renyi entropy accumulation and generalized probability estimation. This yields fully Renyi security proofs. And the power of what we got is that one of the power of the things that we got is a simple single round quantity to calculate. It is also gives us extremely tight finite bound results. And well, I did not point this out, but we also have a smooth max version of it, or alpha less than 1 version. This is also useful for the case for one-shot distillable entanglement, if you're interested. And for the future work, we have a companion work with Thomas Henn using STP techniques to compute this single round quantity for device independent scenario. And then there's also another ongoing work, again, using STP techniques for computing our single round quantity for device dependent protocols. And with that, I'd like to thank you for your attention, and I'm happy to your questions.
Thanks for the nice talk. Are there any questions from the audience? Well, if not, then I can start. So what do you mean precisely when you say that they are tied up to typicality?
Right, so, oops. So that means if you go through the arguments, all the inequalities can be saturated by an IID state, except one single term, where we can show, you can see that if you pick your accept condition to be around the IID behavior, you'll get extremely tight results. So like, because it's around IID behavior, it's like up to typicality.
Other questions? Yeah.
Do you have any additional intuition why like Renyi divergences are preferred compared to other ones? I mean, like you could base your conditional entropies on all kinds of crazy divergences?
Well, for our application, we use this to generate secret key length, and that's for starting with privacy amplification. And up to now, the Rennie version of the privacy amplification is the tightest that we can get. Yeah.
Thanks.
All right. Any more questions? Well, if not, then let's thank the speaker again. And we'll continue in 10 minutes.
Can you hear me? Perfect. Perfect. Thanks.
All right, let's start with the second talk of this session. So now we have Niklas.
Sorry.
Galke, right?
Niklas Galke. Yeah.
Niklas Galke, yeah. Who's going to talk about sufficiency of running divergences. So Niklas, please, floor is yours.
Yes, thanks. So exactly, I'm going to talk about this problem to you, which I've been working on together with Laurits van Luik and Henrik Wilming, both at the University of Hanover. And this problem has an abundance of literature that has looked at related problems, special cases, things like that. I'm not going to run through all of that, but still, I'm going to introduce this problem to you and what we have done in order to attack this problem. So I'm going to start by stating the data processing inequality. Many of you are probably familiar with it. So given you have some quantum divergence and a quantum channel, if you apply your channel to a pair of states, this pair of states cannot become more distinguishable with respect to this divergence that satisfies the DPI. And also many divergences, many quantum divergences additionally satisfy a recovery map result, like most famously due to Petz and his family of Renyi divergences and the quantum relative entropy, which states that if you do not only have the inequality, but actually equality, then there exists a map, sometimes completely positive, sometimes not, that takes you back to the original state, pair of states. Now, the problem that we want to look at is very closely related to this recovery problem, right? So in both cases, we look at pairs of states, pairs of quantum states. And in both cases, we talk about equality of some quantum divergence. So for the recovery problem, what we have is we have given the two pairs of states and a quantum channel that connects the two pairs. And if we then assume that we have equality of, well, suitable quantum divergence, then we get the recovery map. Now, the problem of sufficiency, which is like the name is related to the problem of statistical sufficiency, is that we assume the equality not for a single divergence, but for a family of divergences. But in return, like by strengthening this assumption, we do not need to assume that we already have a channel that connects the two pairs. And then what we want to deduce is that we can actually go from one pair to the other, and then by the recovery result, for example, go back. So this is the problem. I'm going to state it again in formulae in case you prefer that. So first of all, this is the definition of the Renyi divergences that you've been waiting for since the previous talk. And this is the family that we will be looking at, right? So we call a generalization of this classical Renyi divergences, a quantum generalization, sufficient if from equality of the divergences on some open interval for the parameter, you can deduce that you have maps going back and forth between the pairs of states. So I didn't state that these will be quantum channels because we will see that in general you cannot deduce that. But of course, a priori that would have been the hope, right? You would like to get quantum channels. So the main question that we looked at is that, does there exist a sufficient family of quantum Renyi divergences? Because now I have defined this property of being sufficient, but no one tells you that this is actually something that exists. So this is a question that I will be talking about, and I will tell you that in the classical case, they exist, and it's the classical Renyi divergences. And I will also tell you that in the quantum case, we don't know if they exist, but I will give you some results about which one could be sufficient, which one could not. Right, so we start with the classical case, and basically what I'm stating is if you have probability measures, two pairs, such that you have this equality, then these two pairs, also called dichotomies, they are actually interconvertible via positive groups. And how do we prove that? The proof is basically via some kind of normal form. So what we do, we start with these abstract probability measures on some space. And what we construct is we give you a measure mu on this extended real line, like right? So such that we can interconvert this P and Q with this other dichotomy, which is mu, and some absolutely continuous measure. Well, the absolute continuity is a bit tricky, but at least it looks like it's absolutely continuous. And then from this normal form, by taking another dichotomy and going to their normal form, you get the interconvertibility, provided that the Renyi divergences coincide on some open interval, which is basically due to injectivity of the Laplace transform. And this measure mu is constructed by taking this function, which you know from the definition of the Renyi divergences. And then you basically just take the push forward measure with respect to this function, and that gives you this dichotomy, this normal form. Right. So for example, for probability vectors, what this does basically is that you take the ratios of the probabilities of your probability vectors, then you collect all of them that are equal, you sum, right? You can kind of integrate out the level sets of this ratio, and that gives you the normal form, basically. Cool. This is the classical result. But here we are in the quantum conference, so I'd like to talk a bit more about the quantum case. And the first result I would like to show you is some kind of quantum analog of this normal form. It's related to the Cauchy-Emoto theorem, which has appeared in a couple of talks already. And it states that if you have some family of quantum states indexed by some theta, then you can decompose your Hilbert space in this form, right? You have a couple of blocks, and the blocks themselves have a product structure, bipartite structure. And you have some additional conditions, because otherwise this is not really informative. So first is that you can decompose your state in this block form, in this way, right? So you have some probability. Then you have the blocks, which is on the one factor, some rho j theta, some state. And on the other block, and this is the more important part, you have another state, omega j, which does not depend on theta. It only depends on j. So it's some kind of multiplicity, but you can have, I'll change it a little bit. But you can have like different probabilities depending on which dimension you want to weigh. And you have an additional condition on maps which have this family as fixed points, which is that if every map that fixes all of the rho theta simultaneously restricts to a map of this form on each of the blocks, where this channel in the second entry fixes each of the omega j, right? And this essentially makes this decomposition unique in a certain way. Now, if we have this form, what we can do is we can trace out the omega j in each block. And we can also tensor them back. And that gives us a possibility of interconverting the original family with this kind of minimal form of this family that you get by just removing all of the omega j. And in the classical case for probability vectors, if you do that, it actually just gives you back the normal form for probability measures that I explained to you on the slide before. So we have some hope that this might be some tool that you can use in order to prove the quantum case, provided that it's true. So let's talk a little bit about that. So one corollary that you can get more or less immediately from this decomposition that I've been talking about and the minimal form is that you have that two families are interconvertible via a quantum channel if and only if the minimal forms are blockwise unitarily equivalent. So in every block, you have a unitary that maps one family to the other one, right? Because you have this joint block decomposition. And this is equivalent. And the proof basically goes like this. Well, first of all, we know that we can interconvert with the minimal form, right? So we can assume that we are minimal already. One direction is done. The other direction, we take we assume that we have R and S that interconvert between the families. And then we look at their compositions. Those are maps, completely positive maps, that fix all the rho theta or all the sigma theta, however you like. And therefore, by Quashimoto, we have a decomposition of this map that restricts to something kind of easy and kind of simple on each block, right? And then there are some abstract results in C-star algebras in the paper by Cadderson that tell you that, okay, these restrictions to each block, they already need to be mutually inverse unitaries. And then thereby you get this, this corollary. We also have some no teleportation type result, which relates to the Quashimoto form in this way, that if you assume that the blocks that are allowed to be theta dependent in your Quashimoto decomposition, that they are all one dimensional. So basically just a number, and then all the stateness is in the omega j, like the multidimensionality. Then you get that this is equivalent to your family already being interconvertible with classical states. Or in other words, that the rho theta themselves already commute, right? So you can only interconvert commuting states with commuting states. It's not possible to have non-commuting states and interconvert them with commuting ones. And well, another condition that you get is that the family is a family of joint fixed points of some entanglement breaking channel. So some channel that factorizes through a classical system, which is kind of natural from point 2, let's say. So this is kind of no-go result that tells you how to rule out certain divergences, and I will tell you later how we apply that. There's also a property of function which is called complete monotonicity, which we found to be related to this question of sufficiency of a family of Renyi divergences. And for that, we assume that we have this limit, which is kind of the, what do you say, like maybe the max relative entropy or something like that, that this exists. So if you have that, then the following are equivalent. So you have a classical dichotomy that has the same, it has the same Renyi divergences as your quantum dichotomy. And the following function, which is a little bit ugly, but it's okay, is completely monotone, which means that if you take the nth derivative and multiply it with -1 to the n, so you alternate the sign, this is basically like monotone. So alternatingly, monotonely decreasing or increasing strictly. So these also are equivalent. And again, this might be one possibility of ruling out families of divergences, because, well, it relates to the slide before. If you can actually show that this is true for some family of Renyi divergences, then you know, okay, there are classical divergences with equal there's a classical dichotomy with equal divergences, and therefore, by the previous slide, you cannot interconvert. Like it cannot be sufficient, because otherwise you would get existence of interconverting maps between a classical and a non-classical dichotomy, and the non-classical one, well, you can choose it to be non-commuting. We also have some negative results. So the first is that any family of anti-unitarily invariant divergences cannot be sufficient for detecting interconvertibility via completely positive maps, right? That is because, well, you cannot in general convert a state and its complex conjugate via a completely positive map. But if you're anti-unitarily invariant, you cannot, you have the same like Renyi divergences, therefore cannot be sufficient for complete positivity. There's bad news and some good news associated to that. The bad news is that all Renyi divergences that we know are anti-unitarily equivalent. So far there's no chance of getting completely positive interconvertibility. The good news is that all families that we know also satisfy the data processing inequality for positive maps on some interval, right? So we can still hope that that there's a sufficient family for positive interconvertibility via positive maps. So that is what we will have in mind now, right? Completely positive is off the table. We can look at positive. Now, even if we do that, if we assume that we want positive interconvertibility, we can rule out a couple of divergences. So for example, the PETS type quantum Renyi divergences, which are a special example of the standard F divergences, they cannot be sufficient even for positive interconvertibility because there exist the Nussbaum-Scola distributions, which are classical distributions with the same divergences. Same for the geometric one, which is a special case of the maximal F divergence. Sorry, yeah. Thanks. It's just a special case for the maximal F divergences. There we have Matsumoto's minimal reverse test, which again gives you classical divergences with the same classical dichotomies with the same divergences. I don't know how many times I've confused the two terms already. Right. Okay, so these two families, PETS and geometric, we can rule out for sure. They cannot be sufficient. And then there's the last sad fact, which is that the Quashimoto decomposition, which we would hope to be useful for answering the quantum case, is not good in the setting of positive maps, because there are dichotomies for which you have positive interconvertibility, but the structure you get from the Quashimoto theorem is different, has a different number of blocks. So the Quashimoto decomposition is not an invariant for interconvertibility with positive maps, and therefore by itself not the right tool. Okay. We also have some hope, some positive evidence, namely for the sandwich Renyi divergence. I didn't put the definition here because it's kind of complicated and not really useful for what I'm going to tell you. Our intuition is that due to the formula, the words in rho and sigma that you get are sufficiently complicated to get enough information about the relation between the two states out. So what we have for these is that we can show that that in general you cannot find classical distributions with equal Renyi divergences. So the trick that we use to rule out PETS and geometric will not work, right? Second is we did some numerics to check the complete monotonicity of this map F. And also there, so far, we couldn't find an example of a dichotomy where you don't have the complete monotonicity for the sandwich Renyi divergence. And the last is that what we could prove is that if both dichotomies contain a pure state, then equality of the sandwich Renyi divergences actually tells you that there is a completely positive map going from one to the other and back. And here the constraint with the anti-unitary invariance doesn't apply. Well, basically because the two states are pure. So if you write it down, you can see that it doesn't give a problem. So therefore, we think that the family of sandwich Renyi divergences might be sufficient for detecting at least positive interconvertibility. And well, that's kind of the hope that we have, and that is where we would like to look and see if that is actually true. So I have some directions where one would like if one would like to tackle the problem, to answer the question, might want to start. So the first is that if you can find an example of true catalysis, right? So you tensor with a catalyst, thereby you get convertibility, but you know that the original ones were not already convertible via positive maps. If you find that, then you can rule out the sandwiched, the family of sandwich divergences. Another one would be, maybe we just didn't try hard enough to extend the classical proof or the one for pure states to apply to a general quantum setting. Might be a way. We didn't see any way of doing it, but I cannot exclude that we just didn't see it. Another one would be maybe to find a divergence that is not invariant under transposition. So I put divergence here in scare quotes because like a divergence is kind of an information theoretic quantity, right? While the question between positivity and complete positivity is a question about entanglement. So why should the divergence that measures distinguishability of two states be able to tell you something about this like general entangleability question? But still, maybe there's some quantity that is divergence-like that can do that. And the last point is that if we can adapt the Kawashimoto decomposition to positive maps, then maybe that's a tool that you might use to answer the question. And that seems to go in the direction of Jordan algebras. And yeah, with that, I would like to thank you, and I'm open to questions.
Thanks, Nicholas, for the nice talk. Are there any questions? Yeah, over there, there's one. So, yeah.
Okay. Thank you for the very nice talk. I wonder if I can ask two small questions. The first is about the geometric divergences. As you said, that there are you can see them as like a kind of like the Nussbaum score. You can find a preparation method for them, but to my understanding, it only extends for alpha at most 2. So technically, after alpha greater than 2, we don't really know for that. So could it be technically possible that for alpha greater than 2, those could still be sufficient? I don't know if this is the
potentially. I'm not 100% sure about the ranges of alpha that we dealt with in the paper. If you know the book by Hiai on F divergences, we use the same range of alpha that he uses.
Okay.
So if he only goes until 2, well,
to my understanding, it only works until alpha
right.
goes to 2.
Then maybe potentially you can.
Although it would be weird.
Yeah, maybe. I'm not sure. So maybe yes, maybe that's something you can try as well.
Okay. And a second question, if I may. As you said, this is a quantum meeting, but I have a very classical question.
Yeah.
That you had a complete proof for the classical case. What if you ask the same question that you kind of want to transform multiple measures into multiple, like you ask the sufficiency for like similar transformations of multiple, not only 2 but multiple probability.
So the question is if the classical proof extends to a family that does not, like, to larger families than pairs.
Yes. Of course, the same also could be done in quantum side, but that's just beyond.
I don't know. We haven't tried it explicitly. In principle, what you need is so we assume more or less absolute continuity, right? If you have multiple measures, maybe you can just sum them to get something that has sufficiently large support, right? Mm-hmm. And then basically do the same proof, but with respect to a measure that itself is not part of the family, to transform to the real line. and thereby get an analogous result. But I don't know, we haven't tried.
Okay, thanks.
Further questions from the audience? Well, if not, then maybe I can ask a question. So
Sure.
there are also more exotic families or constructions of F divergences and things like that. Have you looked at them, or like have you considered variations of this problem for these divergences?
So, I mean, okay, so there are a couple of families of Renyi divergences that that we didn't look at in particular, like the ones that we dealt with more or less in detail are the pets one, the geometric one, and the sandwiched.
I know, but like even going beyond, let's say, Renyi, maybe you could consider other sorts of divergences. You see if you could study this direction.
Like how exotic, like alpha Z or even more. Like, I mean, that's still some kind of Renyi, right?
Yeah,
but
yeah,
if you
yeah.
include the Z, it's not anymore. It's a family of families, right?
Yeah.
Which includes the sandwich and the pets. So in some sense, you would have more hope, right? Especially if the conjecture about the sandwich one is true, it's true about the alpha Z. More exotic than that, I don't know. Like, do you have something specific in mind?
Yeah, no, I was thinking if you go beyond Renyi divergences,
okay,
you can consider F divergences.
Okay, well, so about the F divergences, the no-go ones for pets and geometric, well, they don't really depend on restricting to the Renyi subfamily. Let's say they work for the general F divergences. Maybe one thing that one should say is that if you take the F divergences, actually what you can show, which has been shown by Matsumoto, is that they are sufficient for determining like convertibility. So if you have like dichotomies with classical dichotomies, such that the maximal doesn't make a difference. Like the F divergences, all F divergences satisfy an inequality. You can go from one to the other via a stochastic map. If you restrict to the Renyi, that breaks down because of catalysis and additivity. You become additive, so catalysis rules out this possibility. But still, in the quantum case, like the fully quantum case, also the full family of F divergences that we know, maybe apart from measured ones, I don't know about those, but it's maybe more a classical quantum thing, you can rule out.
Thanks. Okay, then I guess let's thank the speaker again. That's it for the session.
Hey, how are you? Oh, is this? Too many options. Oh, excellent. Yeah, right. Use all three. Is that what they call? There was only one button. Yeah.
I appreciate it. Does this work? It appears to work. Right. Yeah. They need to give shares with them. You should just start playing. Yeah. I want to ask like, what is the most like contract? Has it ever come to which is my standard. Are you feeling any better? I don't have a fever anymore, and I don't have a headache anymore. My throat is still scratchy. I have no idea, but if COVID is super short, it seems that I've mostly recovered in a day, but since I don't know what it is, it's like wearing the mask. Very conscientious. That's nice for all of us. I mean, even if it's not COVID, yesterday wasn't pleasant, so I don't want you guys to get it. I'm a bit worried about Tim because we're like sharing a hotel room, so whatever I have, there's a high likelihood he will get it.
I asked him yesterday whether he thinks that you will contract it. I said, no. It's old age. I'm younger than him.
Well, I think Tim and I are like 1 year apart. So. But I'm old in spirit. That's probably the. Yeah. Sorry, what? Where is that?
Maybe not. So, you can get everything in this talk without OHA.
That's mean to what?
But there's a much nicer, the most beautiful version of our in collaboration with OHA for sure.
I just remember we were talking about like Holberg and Jung, but I don't remember the other name.
Yeah. So yeah. So this but illustrated
Jim? Oh yeah. We like cold female children about something. Does that work? Very responsible. Just like 13
Oh, since we were, that was thinking about it. Yeah, that was with me. So what did you have? Who has good state testing? But we do from time to time. Yeah. You do that with like temperature that you. It was using like but yeah.
It might be fun.
But Fran also doesn't do testing of themselves. Yes, so we were thinking about and then we're like, oh wait, let's solve that. I mean, if you're interested in Chattanooga states, yeah, so that's what we're interested in because you said, like Daniel said, you guys have like a simple proof. Yeah, there's that you can't do. Yeah. Oh, okay. Yeah. Yeah. So we haven't. I mean, you know, like show a project. Sure. Yeah. Maybe we can. Yeah. So it was me, Shiv, and Launch now there. Typically, he doesn't only want stuff. Yeah. Yeah. Yeah, it's a very natural question. There's different classical Hamiltonians. There's some like arguments with yeah, there's an old paper about the 20th era in classical. We might have probably 2 minutes or so.
All of them. I think once these people have settled, then we can start. A lot of people coming right now. Let's Okay, then welcome to the afternoon session. The first talk of this session is by Joseph Sloat on quantum Boden-Blastille inequalities and learning low degrees quantum observables. Please.
All right. Thanks for the introduction and thanks for coming to this session. I'll be talking about a pretty generic problem in quantum computation and some recent entrance of some harmonic analysis inequalities that have led to some pretty exciting speedups. And so this submission to TQC is actually a compendium of works. So the first one is actually just by Alexander Volberg and Haonan Zhang. and then a follow-up where I joined with Ohad. So these are my collaborators. And so let me develop the problem. So lots of times in quantum computation, you have some unknown channel here, and then you're interested in what happens to a state when it goes through this channel. And so you have a fixed measurement you're doing at the end. So if we call the channel together with this measurement A, and let's take A to be a Hermitian operator, so this whole thing is von Neumann observable, we might be interested in learning a description of it so that we can predict what new states will be observed to happen. So the goal is to learn an approximation to A in Frobenius norm, which is sort of sufficient for average case accuracy over input states, when we're promised the following. A is low degree or local. So here we have this little bit clunky notation. This is just indexing over all Paulis where the number of non-identity entries is less than or equal to D. So here A is degree D. And this notation here is just our product of Paulis, one for each qubit. And this notation here, this is just a number. This is the coefficient on that Pauli operator. So again, low degree, degree D, size of Q is the number of non-identity entries. The other promise we'll have is that A is bounded by a constant. So we're interested in observables that don't run away in energy as the number of qubits grows large. And under these conditions, recently there's been kind of a flurry of effort. So I'll now briefly go over the setup and how it's related to classical learning. Okay, so we'll call our notation. The general approach is something called Fourier sampling, which actually is developed from classical literature. The idea is that if we can learn each of these coefficients to high enough accuracy, we've learned the operator. And you can rewrite this coefficient. So here's the definition. You can rewrite it in this way, where rho is chosen from a particular distribution of states. What that distribution is doesn't matter too much. But the point is that this quantity here we can estimate experimentally, and this quantity we can just compute because the distribution is our choice. We're the ones doing the learning. So with that setup, we find that we can form an empirical Fourier coefficient here, where we just choose some large capital N, and with these rho j's chosen from our distribution, capital N of them, we can form our empirical Fourier coefficients for each coefficient that matters. And I'm sorry for this alpha, that should be a capital Q. Okay, so Fourier sampling is an old technique that has worked both in classical learning and quantum learning. Now, with this perspective, we can ask, how many samples do I need? What's that capital N? And if we think as on the back of the envelope here for a moment, we could say, okay, well, usually if we want to know how many samples, we can ask how many possible sufficiently different observables are there? So let's think about the cardinality of an epsilon net on this set of observables. Well, A is degree D, so there's a Pauli in N parameters to estimate. And A is also bounded, so each coefficient lives in some interval. So epsilon cardinality is something like, size of this interval cut up into little pieces to power n to the d. And a rule of thumb with these single outcome measurements that we're doing, we optimally are cutting our space in half each time. So how many samples do we need? It's log of this quantity, which is some constant, which is a function of epsilon, times n to the d. So nothing too surprising in terms of sample complexity. Okay, so how did we do on the back of this envelope? Well, we used the locality promise, and we used the bounded operator norm promise. And actually, this was understood to be kind of the best way to do this kind of learning task for around 30 years or 25 years. Except it's not. It's not even close, because this back of the envelope computation doesn't fully appreciate the interaction of locality and boundedness. So the actual number of samples is logarithmic in n. Okay, so how could this be true? It comes down to an old inequality by Bonin, Bust, and Hill, and actually a discrete version of it. So let me describe it now. We take a d-local operator, and we consider a certain LP norm of the Fourier coefficient. So those numbers in front of each of the Pauli operators. This is just explicitly what I mean by this LP norm. And the inequality says that this LP norm is bounded in a dimension-free way. So you'll see this constant here does not care about the number of qubits by the operator norm of A, which we've bounded by a constant. So what that says is that this LP norm for p slightly less than 2 is bounded by a constant in our setting. And that implies that the spectrum, or the collection of these coefficients, is approximately sparse. So this is just a cartoon of all of the local operators in our expansion of A, and very few of them are sort of important. So, and I'll talk about this more in a little bit. It was first realized 2 years ago in the classical literature that this approximate sparsity was enough to reduce sample complexity from polynomial n to log n with the following technique. You do Fourier sampling just as before, and then you say, okay, if the empirical Fourier coefficient, such as this one, is very small, then actually the variance on my estimate for that coefficient is larger, probably, than the true value itself. So I should set it to 0 instead. So the update to the naive Fourier sampling algorithm is simply to set some threshold, a very, very carefully chosen threshold, and then zero out all of the empirical Fourier coefficients less than this threshold. There's a lot of details in there, there's a lot of estimates. I won't go through them now, but this idea is due to actually a classical paper by Eskenazis and Ivanisvili at Stock 2022. I'll mention them in greater detail later, but that's sort of the idea of how do we get from poly n to log n. It's this approximate sparsity. So the key takeaway is that if you can prove Bonin-Bust-Hill inequalities in your space, be it in a quantum space or classical space or some other space, you get approximate Fourier sparsity. And that's sufficient for this learning improvement. Okay, so just some brief history. Lineal, Mansour, and Nissan, this is this landmark paper from the early 90s. They introduced, or sort of are understood as one of the early introducers of classical low-degree learning via Fourier sampling. And they get the sample complexity. Eskenazis and Ivanisvili, 2022, noticed that this hypercube BH inequality could actually be used to get this massive improvement, such as this log n sample complexity. Then Huang, Chen, and Preskill last year were able to quantumize this argument, and they gave a first proof of this non-commutative quantum BH inequality that you saw on the last slide. And so this is very exciting. Volberg and Zhang, then around the same time, produced a very short proof of the same inequality, this slightly improved constant. And finally, this year, along with myself and Klein, we extended this collection of inequalities to qubits, not just qubits. And this ended up being rather difficult. So we actually had to reach deeper down into approximation theory and prove some fact about high dimensional polynomials and some other dimension-free type inequalities, which I hope to have time to discuss at the very end. But what I'd like to focus on first is this short proof, because it contains a principle that says if you want to prove an inequality about some local Hermitian operators, it's kind of, these things are scary, they're non-commutative, maybe these the different basis elements interact in a kind of terrible way. sometimes you can completely ignore the non-commutativity. There's a way to pass sometimes to a commutative world and still get the result you want. So I think I'll have enough time for that, and we can spend as much time down here as is available. Okay, so the quantum BH proof of Volberg and Zhang. The idea is, like I said, circumvent non-commutativity. And we want to use this. So this is sort of already in the literature. It's a classical one. Here, instead of a quantum operator, we have a Boolean function. And we know when we write it as a multilinear polynomial, it has degree at most d. And we want, again, to bound this special LP norm by the supremum of f. This just means is less than or equal to up to a constant depending on d only. So how can we relate this inequality to the inequality we want to prove, which is non-commutative? The idea is to design a Boolean function f on 3 n variables such that 2 things hold. The first is that we can relate the LP norm of the coefficients of our operator A to the LP norm of the Fourier coefficients of f. And 2, we can control the supremum norm of f by the supremum or operator norm of A. So if we have both of these properties of our Boolean function, we can have the following string of inequalities: control A, LP norm of A by LP norm of coefficients of f, use the hypercube Bonin-Bustill inequality, and then again, control the supremum norm of f by our operator norm of A. Okay, so this Boolean function here seems kind of magical. How could we have such a function? It ends up being not so bad. Okay, so there's our goal. Again, as I said before, we want these 2 properties from f. So let's take our 3 n variables and we'll organize them by x, y, and z. The x's will correspond to Pauli x's, the y's will correspond to Pauli y's, and the z's will correspond to Pauli z's. And it's actually easiest to explain this construction by example. So let's just look at this one for now. If A is some alpha coefficient times this Pauli operator plus beta times this Pauli operator, what we're going to do is we're going to go through each operator, and if it was an I, we will replace it with 1, this is the constant 1. If it's an x, we'll replace it with this variable. So it was in the 3rd spot, so it becomes x3 divided by 3. And same with y, y4 divided by 3, z, z5 divided by 3, and so on. So it's just really an explicit rewriting of the Pauli operator, or Pauli decomposition into this Boolean function. And we can think about what happens. So immediately, I'll get to that key fact in a sec, sorry. So immediately we see that the coefficients on, the Fourier coefficients on f are very closely related to the Fourier coefficients on A. So you get at most division by 3 to the d, because that's the maximum locality of A. And so they're within 1 and 3 to the d of the correct number. 3 to the d is dimension free, so that's all sounding good. And that actually gives us immediately this piece here. And let's talk about this key fact. How do we get this piece? Well, for any point in the hypercube, this 3n variable hypercube, there is a row, depending on that point, there's a state, fully normalized state, such that its tracial inner product with A is, or expectation value, is exactly f of x, y, z. And if you believe that for a second, you can see that that gets us exactly the second inequality, because the supremum of f is just a range over all of these. Each point here corresponds to a state you could imagine looking at over here. So the supremum, so the supremum has to be larger. Okay, or the operator norm has to be larger. Now, what is this state? It's a kind of a cute magic state looking object. The point is you can you can encode the value of x, y, and z together in the same qubit because, and this I won't spend a lot of time on, but because essentially the eigenvectors of the x, y, and z operators miss each other. So when you evaluate this quantity here using these states, this is like a direct substitution into the function f. Okay, so that's kind of it. That's the proof of the qubit. Sorry, that should say qubit Bonin-Bustill inequality. And I think it'd be exciting to see how this kind of passage from non-commutative to commutative, how this idea can be used elsewhere. In the remaining time, I'd like to just briefly talk about how to extend to qubits. So everything becomes more annoying. Now, instead of a Pauli basis, we have Heisenberg-Weil matrices. So these are the clock and shift operators. Look at products of these. You get a basis for matrix algebra on level K qubits. And oops. Okay, and the reduction argument still works. We can pass to some commutative space. It's much more intricate though, because the eigenspaces of various operators in the spaces are not orthogonal. And that's because these operators are not exactly anti-commuting. But you can do it, you can get this reduction, and it reduces to a commutative Bonin-Bustill inequality, but it's no longer the one for functions on the hypercube. It's one for functions on products of cyclic groups. So let's go into the literature and see what's known about that. So here's just some notation I'll use for cyclic groups. They can be represented as roots of unity. I'll call this space omega sub k of n. When capital K is 2, that's just the hypercube. Okay, so what's known? So I've already talked about Bonin-Bustill inequality for commutative polynomials on the hypercube. It's this guy. The original Bonin-Bustill inequality, all the way back in 1931, was for the polytorus. So this is complex polynomials on product of circles, Cartesian product of circles. And what we need to do the qubit version is we need a function, we need a Bonin-Bustill inequality for functions on this domain. And you'll notice that this qubit version is like the interpolating case between the hypercube and the polytorus. But sadly, it doesn't work the same way. So these two endpoints share a proof approach, but the middle guys resist the same technique. Happy to explain why, but it's rather frustrating. But that's okay. We push for it anyway, and I can just state how the proof goes. So here's just a little bit of notation to talk about any function on products of cyclic groups can be written as a polynomial, just like in the hypercube case. It's no longer multilinear. It can have larger individual degree. And so what you do is you write this down, and you now consider evaluating this polynomial not only over the discrete roots of unity, but over the whole polytorus. And so the idea is maybe we can use the original Bonin-Bustill inequality to get this comparison for this polynomial. Here we're taking the supremum over the whole polytorus. And if we can find a dimension-free comparison of this kind, where we say that the supremum over this lattice of points, these products of roots of unity, if it controls the supremum over this whole product of circles in a dimension-free way, then we win. And that's exactly what we're able to prove through, I think, kind of a enjoyable probabilistic argument. And I think that's it. Thanks so much.
Okay, so are there any questions? Yes, I don't know if there's microphones. Yeah, okay, it's coming.
Could you explain why the torus resists the same approach?
Yeah, like why the interpolating case is like so much harder.
Right.
Yeah, so the way Bonin-Bustill proofs go is you take this, you take your polynomial, and then you pass to some symmetric linear forms, and you prove the inequality in this like somewhat expanded world, and then you need to go back to the original polynomial. And there's this thing called so it's called this like polarization inequality. Essentially, if you have this linear form, in the true case, all of the variables are equal to each other, but in your linear form, you like made several copies of the same collection of variables, and in order to go back, you rely on a comparison that is free for both here and here. So how to say it? It's something like the supremum. It boils down to the following fact: the supremum over the complex disk is always on the boundary. The supremum over the solid cube is always on the boundary because these polynomials are linear, so it's convex. But here, it's not so clear. So we know that the supremum lies somewhere on the circle, but it may not lie at one of these special points. And so essentially, this domain, unlike the other two, is not the total boundary of its convex hull. That's like the one sentence reason why it doesn't work.
Okay, more questions?
Is there like a rule of thumb for when I can expect the Bonham-Blust-Hill inequality to hold? Like, so when is it true that having a low degree Fourier expansion and being bounded leads to Fourier sparseness? Like, is this true for the standard Fourier expansion of real valued functions, for example?
Right. So the space would be, I guess, like the solid cube.
Yeah. Yeah, I'm thinking like periodic functions on.
Yeah, I think it will. That's a good question. I have the sense now that it will generically hold like this Remez inequality seems to give things for free, relatively for free. Though the question of the constant, so how much is this constant depending on D, that will change a lot. So maybe one other comment I'll make is that for both of these endpoints, the amount you lose in this comparison of LP norm to supremum norm is like C to the square root D ish. But in the middle here, we only got C to the D. So.
My question is related to what you just said. Are these constants on D tight?
Yeah, so no one knows. It's like really, really hard. I have some colleagues that believe it might just be a number, like it might be 7 for the hypercube. Yeah, yeah, or at least polynomial. Like extensive computer experiments suggest that it really should not be exponential in D.
Right.
Yeah.
Okay.
So
thank you.
Fun open problem. Maybe on the flight home. Yeah.
Any other questions? Okay, maybe let me also ask one. I mean, you now did like qubits and qudits. I mean, can you do any infinite dimensional version where maybe like you introduce some energy cutoff and displace the?
Yeah, that's a wonderful question. I thought like only vaguely about this. It seems like these energy cutoffs don't behave super nicely. You can have like norms explode when you do that. So maybe there's like a nice way, but I'm not familiar enough with CV. So yeah, if like somebody wants to help with that, that'd be great.
Very good. Last chance for a final question. Okay, if not, then let's thank the speaker again.
Thank you.
Then see you in 5 minutes.
Now, yes, it works.
Okay, time to settle down and enjoy the next talk. So the next talk will be by Francisco Escudero Gutierrez, and it will be on learning low-degree quantum objects.
Yeah, thanks for the introduction. So this is a work jointly done with Srinivas Arunachalam and Arko Paldut, who are there sitting in the audience somewhere, and Carlos Palazuelos. So I will start by introducing a classical version of the problem of low-degree learning. So this dates back to the work of Liam Masur and Nisa, who gave an algorithm to learn functions defined on bits that take bounded values and have degree d. And they saw that with n to the power d uniform samples, you can learn these functions. So let me be a bit more precise with this notation. So having degree d means that when you look at the function as a multilinear polynomial, when you look at its Fourier expansion, this expansion is truncated to those monomials of degree at most d. So it's the natural notion of being low degree. And random samples means that f of x is picked in a way such that x is picked uniformly at random from the Boolean cube. So this is the model they studied, and they proved that with only n to the power d uniform samples, you can learn these functions. And this is interesting because of two things. The first one is that with this structure of being low degree, you can beat by far the learning algorithm that you would use if you had no structure, because this learning algorithm would require 2 to the power 2 to the n random samples. And they also gave a first application of this low degree learning to the problem of learning AC0 circuits, which is a family of constant depth circuits. Since then, there is many works using these ideas of Liam Masur, but it took a lot of time, 30 years, to improve the algorithm itself. So there were many applications of these ideas, but there were no improvement on the algorithm. And this was done by Squids and Abenesvili 2 years ago, and showed that with only log-n samples, you can learn these functions. And the reason that we took so long to improve this is because we were missing a tool, and this tool came from another field, which is functional analysis, and the tool is Bohn-Engels-Angel inequalities. So since then, many people have tried to extend these ideas of low-degree learning using Bohn-Engels inequalities to other places. In particular, several authors have tried to prove new Bohn-Engels inequalities and say something about learning quantum objects. For example, you can go to the talk of Joe that gave just before, and he explained how you can use von Neumann square inequality to learn low-degree observables. There is also works by Juan, Chen, and Preskill, and the other works are by the group of Joe, Keller, Slote, Wolver, and Sang, and these all focus on learning observables. But what we did was extending these ideas of von Neumann square inequality to do low-degree learning to other quantum objects, and to do that we had to prove new von Neumann square inequalities. So let me highlight two of our results. The first one is that we proved a von Neumann square inequality for quantum channels, which allow us to learn low-degree channels. And we also proved a von Neumann square inequality for completely bounded polynomials. And because of the link of completely bounded polynomials with quantum query algorithms, this can be used to learn quantum query algorithms. This is going to be explained more in detail in the next slides. But let me say before that we also have more results that I don't have time to talk about. I will just mention that we can also learn efficiently other low-degree objects, such as unitaries, Pauli channel, states, bounded functions encoded in unitaries, or Boolean functions. So now let me focus on the result of channels, and let me tell you what is a low-degree channel. Let me tell you a bit about physics. So we are going to consider end-to-end qubit channels, and we are going to look at them through the lenses of the Pauli expansion. So you can decompose a channel as a linear combination of these maps P.Q, where P and Q are tensor product of Paulis, and this expansion is known as the Pauli expansion, and this is somehow the generalization to channels of the Fourier expansion of functions. So given that we have this expansion, we can naturally define degree, and we define degree in the analog way to the one that we use to talk about bounded degree classical functions, and is that we say that this channel has degree at most D if this expansion can be truncated to those pairs P and Q, such that P and Q act non-trivially on at most D places. So they are identity almost everywhere, but on at most D places. And this is also very natural from a physical point of view, because this means that your channel can be decomposed as a linear combination of local things, of terms that only act on a few qubits on its time. So this can be also called being D-local. So this is the object that we want to learn. And now let me tell you a bit of computer science. Let me introduce you what is our learning model. So in the learning model that we have is a query access model, where we are able to choose an initial state on n plus m qubits, so an extra register, and we are going to apply the channel tensor identity, and then we are going to measure. So this is what we call making a query, and this is our unit of computational effort. So something important in this query access model is that with only one query, you can prepare the matrix defined by the coefficients of the Pauli channel. So something important is that this matrix is very nice because it's a state, meaning that it has this one and it's positive semi-definite. And something even better is that you can prepare this matrix with only one query. This was proved by Bao and Zhao, and the proof is very simple. So let me depict it. So let's say that these are the qubits where we connect with the channel. So what we are going to choose as our initial state is just the state that you get when you duplicate the number of qubits and you entangle every of the original qubits with one of the new ones with an APR pair. Now we apply the query, we apply the channel tensor identity, and we get to the choice state. And once we are in the choice state, we just have to change the basis. We just have to apply a unitary that is independent of the state, and we will get to the state defined by the Pauli coefficients. So now when we are here with only one query, what we can do is measure in the computational basis, and thus we will be able to sample from the diagonal of this matrix with only one query. So the diagonal of this matrix defines a distribution that we can sample once using only one query. That is going to be important for us, and essentially that is the way that we access the information about the channel. So this is our model of access to the channel, but we also have to define what is being a good approximation of the channel. So to do that, what we are going to consider is a 2D distance. So we are going to consider the distance between two channels as the normalized Frobenius distance between the corresponding Choi-Minkowski representations of the channel. And maybe this is already giving you some information about this being an average case distance. And if you have worked in physics, this of course have a meaning for you. But for the rest of this talk, what we're going to use is not this definition, but an equivalent one given in terms of the Pauli coefficients. So what is going to be important for us is that we have this equality, which is somehow a parser-verbal identity for quantum channels that tell us that this 2 norm can be expressed as the 2 norm of the coefficients. So if we can learn the coefficients, we will be able to learn the channel. So the complexity measure that we're going to take into account and the task is going to be the number of queries to the channel that we need to learn it up to epsilon error in this distance. So this is our setup. This is what we want to do. And to do that, we need the Born-Bosman inequalities, which is a bit of math. So now let me introduce it to you. So what we prove is a non-commutative Born-Bosman inequality that says that for an n-qubit degree D channel, what we have is that the sum of the powers 2d over d plus 1 is at most a constant to the power d. And let me briefly explain why this is interesting from a mathematical point of view. This is for 2 reasons. So here we have 2d over d plus 1, which is smaller than 2. Just a bit smaller, but this is smaller than 2, and that is very important. And here we have something that does not depend on it. So why is important for this to be smaller than 2? Well, if it was 2 by a parser-verbal identity argument, then this sum could be upper bounded by 1. And if you had that upper bound for the sum of the squares of the Pauli coefficients, then you can translate it to an upper bound of this sum by using Holden inequality, but that upper bound would depend on n. So the interesting part here is that this does not depend on n, and here you will have a power that is smaller than 2. That is interesting from a mathematical point of view. Similar results has been applied in many places in pure math. And now what we are going to do is to try to explain why this is also important from an learning algorithm. So this is important because this is going to mean that the 2 error that we would make when we neglect all the small Pauli coefficients is going to be small. Let me explain why. So let me consider the sum of the squares of the Pauli coefficients that are smaller than a value epsilon prime that we are going to fix a bit later according to our epsilon and our d that we introduced before. So the thing that we are going to do to upper bound this, to control this contribution of the small Pauli coefficients, is to take these 2 and divide it in 2 parts, in 2d over 2 over d plus 1 and 2d over d plus 1. So now this is clear why we wanted here something that was smaller than 2 in the exponent. Otherwise, we would not be able to do this step. And given that we separate this in 2 parts, we are going to take the part corresponding to this term, and we are going to say that it's upper bounded by epsilon prime, so we just can get it out. And the rest is something that we can control. We can go to the Born-Bosman inequality that we have introduced and say that this is at most a constant to the power d. So we have this, and now what can we do? We can define a notion of being small, a threshold that only depends on d and epsilon and ensure that this is small. So what I mean is that by choosing epsilon prime like this, then we would upper bound this all this sum by epsilon. So this means that the small Pauli coefficients contribute in a small way. And here it's important that this epsilon prime does not depend on n. And that is going to be the key of why our algorithm is not going to have a complexity that is independent on n. So this gives us a recipe. So first of all, if we can detect which are the big Pauli coefficients, meaning bigger than epsilon prime, and then we can learn them, we would be able to learn the channel because the rest of the coefficients are neglectable thanks to this argument. And given that what we mean by big is something that is independent on n, we are going to be able to find those big Pauli coefficients just by sampling from the Pauli coefficients, which is something that we can do with one query. And we are going to be able to do that just a few times, a number of times independent on n, because what we mean by big does not depend on n. And then we just have to learn individually every of those coefficients, which are going to be not too many. And then we would have a good hypothesis to say that our channel looks like that. So that is how our algorithm works. Our algorithm works in 2 steps. The first one is detect the big Pauli coefficients, which we can do just by sampling from the diagonal of the Pauli coefficients. And whatever we have sampled in a few samples, we will say that are the big coefficients. And you may say, okay, now you're only looking at the diagonal, but what happens with the big coefficients that are not in the diagonal? Well, that is not a problem, because if a non-diagonal coefficient is big, then given that you are in a positive semi-definite matrix, the 2 corresponding diagonal coefficients are going to be big. So in this process, we will have found with a few samples all the big coefficients. And again, I want to say that these few samples mean that a quantity that is independent on n, because what we mean by big is not dependent on n. And now, in the step 2, we just learn every of these coefficients. And we can do that in a very simple way using a swap test. Maybe this is something that I don't have time to explain, but maybe some of you know that Montanaro and Osborne, in the paper of quantum Boolean functions, they propose an algorithm to learn the Pauli coefficients of unitaries. You can do something very similar for channels, and it's based on a swap test as the routine that Montanaro and Osborne proposed for unitaries. So now that we have detected the big Pauli coefficients and we have learned them, we just have to say that our hypothesis is going to be the one given by setting all the big Pauli coefficients to whatever we have learned in the step 2, and the rest that have not been detected as big and thus are small to 0, and everything is going to work thanks to the fact that one scaling inequality allow us to neglect these small Pauli coefficients. And the complexity that you get is something that does not depend on n, is 2 to the d squared, and this beats by far the general lower bound that you would have if you didn't have any promise on the structure of the channel, which is 4 to the n. So this is all I wanted to say about quantum channels. Let me briefly explain you how can we use Von-Neumann inequality to learn quantum query algorithms. So there was a result about this implicit in the literature, putting together a few famous results. It was not explicit, so I'm going to explain it now. So let me be more precise about what Eskenazi and Ibn showed for D-forms. So for D-forms, they showed that with these many uniform samples, you can learn them. And here, what I mean by a D-form is a polynomial where you can divide the variables in D blocks, and the polynomial is linear on every of these blocks. So for these kind of forms, in particular, the result is more general, but in particular, they showed that they can be learned with these many samples. And this log n looks very good. D squared is not so bad. And now we have to control this. And one may wonder, can we? Yes, we can do it for free because of the classical Von-Neumann inequality for the forms, which says that if we are bounded on the infinity norm, meaning that we take bounded values when we are evaluated on these scalar strings, then this norm, which is the d2d over d plus 1 norm of the coefficients, can be bounded by a constant that does not depend on it and depends only polynomially on d. So this is what we have, and this already implies that you can learn bounded forms with a number of queries that is not too, no, a number of samples, sorry, that is not too big. And this also links to quantum query algorithm, because Beers, Bullman, Cliff, Mosk, and De Wolf more than 20 years ago showed what is known as the polynomial method, and says that if you have a quantum query algorithm that in every stage, in every queries a different block of variables, then the amplitudes are going to be described by this kind of forms. So putting everything together, you get this result that with poly d to the power d log-n samples, you can learn this kind of quantum query algorithms. Now the question is, can we do better? And the answer is yes. What we're going to use is that the result of the polynomial method can be more strong, can be stronger. You can have more structure if you know that you come from a quantum query algorithm. And then we are going to use that extra structure to improve the Von-Neumann inequality. So this extra structure is that quantum query algorithms amplitudes are not only bounded, but they are completely bounded. What do we mean by this? So what we mean by this is that Anurag Chalamrieta and Palazuelos showed that if you have a D-query quantum algorithm, the corresponding form is not only bounded when you evaluate it on -1 and 1s, but also when you evaluate it on matrices that generalize the -1 and 1s, on orthogonal matrices of any dimension. So you pick your form, you evaluate it on orthogonal matrices, and if you take the operator none, that operator none is going to be at most 1. So this is somehow saying that you are not only bounded when you are input one-dimensional objects, but when you are input any dimensional objects. And of course, this is stronger than saying that you are just bounded on the infinity norm, and maybe you can use this to improve the Bonem-Bloch constant. And indeed, you can. What we could show is that under this promise of the form being completely bounded, the 2d over d plus 1 norm of the coefficients is at most 1, which is the best that you can get. So just putting these two things together alongside with the result of Ashkenazi and Ibanez-Vili, what you get is that with only d squared locking samples, you can learn the quantum query algorithms that we introduced before, which is better than the poly d to the power d locking samples. And that's all I wanted to say. Thanks for the attention.
A lot of time for questions. Does anyone have one? Oh, yeah.
In the last talk for the BH inequality to apply, there was a constraint on the norm, but I didn't see any of that in the first part of your talk. So is there any difference, or is it implicitly assumed?
Can you repeat the question?
For the BH inequality to be valid, in the last talk, there was a constraint which says that the norm has to be bounded. Do you agree with that? Or?
Oh, you mean that in the, for example, in the channel case, I didn't say that the norm was bounded.
Yeah.
Yeah, but that is because for free, when you have a quantum channel, you are bounded in the infinity to 1 norm.
Okay.
Because you are trace preserving and so it's somehow for free. Okay. But in fact, our Bonem-Bloch inequality for channel is not a Bonem-Bloch inequality for channel, it's a Bonem-Bloch inequality for super operators that are bounded in a certain norm.
Okay, I see.
Are there any other questions? Yes, over there. I think it comes from behind.
Hi, I was wondering if the channels that you consider, it seems like they have to be like n qubit to n qubit channels. Do you also, can this also be generalized to if you have the number of outputs in your channel is not the same as inputs?
Yeah, I think that the same argument that we use for the proof would apply. And in fact, it's the same argument as Joe explained, but it's a bit more generalized.
Oh, okay, just because you're like the poly decomposition you use is like, it's like the Krauss operators sort of.
Yeah.
But they're square, like the poly operators are square, so.
Poly operators, I don't know what you mean by that.
Oh, yeah, sorry. I think just like how you wrote your like poly decomposition, yes. It seems to only hold if the channel is like n qubits to n qubits.
Yeah, maybe, but yeah, I don't see why this could not be applied for end-to-end. Maybe you have to tweak it a bit, and maybe you have to work with a different way of considering the Pauli decomposition. But
like, I guess another way that people look at it is with this, like the Pauli decomposition just of the Choi state itself.
Okay.
Is there a reason you didn't do that?
Yeah, I don't know. Like we consider the Pauli decomposition that was introduced recently by Bao and Zhao, and so how this is the one that has the nice properties that behaves like the Fourier decomposition for bounded functions. I don't know if other Pauli decompositions also have these properties.
Thank you.
So I have a lot of time. Anyone else has questions? Very good. First step behind you.
How about if you don't have access to, let's say, if you don't have access to auxiliary systems, do you think similar results could hold?
So I think that probably you can do something. So I think I would have to think, but I think that, for example, the Fourier sampling, the Pauli sampling part can be replaced by paying a factor n. But yeah, it's a bit technical, but I don't know if the swap test can be replaced, meaning that I don't know if you can learn the Pauli coefficients efficiently. I guess so, but I don't know.
So if you set t equals n, you don't recover the naive bound. So
No,
do you
no.
think that d square can be improved to d?
Yeah, that's a good question. So we don't know much about the lower bounds. The best lower bound that we get is the one that you have suggested, just saying if you consider n equal to d, then you get a lower bound for to the d. I don't know if you can improve the exponent to d instead of d squared. It's a good question, but usually these are hard, and I think that in the classical case, in the problem that was analyzed by Eskenazi and Ivanisvili, we also have a big gap.
Very good.
Yeah, thanks. I was trying to think of like natural examples of low degree unitaries and channels. Like all I could think of was like juntas. Do you have other like natural families of say low degree unitaries?
So yeah, so this is a bit of an issue, but I think that a good example is if you consider a Hamiltonian that is local, you can see in short time evolution, you take the Taylor expansion, and that is going to be low degree approximately. Not exactly, but approximately. And that is maybe a setting where these kind of objects can arise naturally. And I also can imagine that, I don't know, having a non-two interacting channel can make sense in a lab, which is being the local, I would say.
Got it. Thanks.
Any final short question? Doesn't look like it. So let's thank the speaker again. And then let's meet again in 5 minutes. Okay, then let's continue with the third talk of the session. And it's titled Information Theoretic Generalization Bounds for Learning Quantum Data. And we will have the pleasure to listen to Matthias Caro.
The mic. Can people in the back hear me? Cool. All right. Hi, everybody. My name is Matthias. I'm a postdoc at FU Berlin. And I'll be telling you about joint work with Tom Gur, Kambiz Rosé, Daniel Stolk-Franke, and Satya Subramanian. Sorry to say, this talk will not have Boden-Blast-Hill inequalities. It has other nice stuff, though. So what I'm going to talk about today has the following background. And this is a significantly oversimplified cartoon of how I think about supervised machine learning. And first, I'm going to show you a purely classical picture. So the purely classical picture is that supervised machine learning is a two-phase process. The first phase is that of training. So in training, you feed labeled training data into your model. Then you train your model. This is some kind of optimization loop during which you update some parameters, typically via some gradient descent or something like this. And then afterwards, you've got a trained model with an optimized parameter setting. So think this is maybe a neural network where you fix the weights, or it's some kind of support vector machine where you fix your hyperplane in feature space. Then comes phase two. Phase two is about figuring out how well you actually did in learning. So phase two is the testing phase, where I'm giving you a new data point without showing you the label. But it is kind of similar to the first training point. So it's not one you've seen, but it's generated from the same data generating process. And now we feed that to the model that you trained, you predict the label, and I then compare that to the true label. And okay, if you learned well, then hopefully you got the right label. So if you think about this cartoon and where to make it quantum, there's different options. And essentially you can make everything here quantum. So you can make the training data quantum, both the inputs and the labels. And you either can or even have to, depending on what part of the data you made quantum, change the model itself to be a quantum model, and also the updating procedure might be a quantum procedure. But other than that, the idea should remain the same. So you still have some kind of training phase, and then you have a testing phase. So this is a very naive perspective. But in this very naive perspective, there's a pretty important concept, which is the concept of a generalization bound. So in classical machine learning, generalization bounds are kind of the mathematical way of asking, how well do you do on data that you haven't seen? So that means that we're asking, I have trained so that I achieve a good performance on my training data, and then I want to find out, do I also achieve good performance on testing data that I haven't seen yet? And the crucial thing here is that we want to bound the difference between test performance and training performance. This is typically called the generalization error. For the purposes of this talk, I'm always going to talk about the expected generalization error. So here we have an expectation value, and you should think of this expectation value as being over the training data that you saw. So I imagine that the training data is sampled from some random process, and I want you to achieve a good average generalization performance. In classical machine learning, there's loads of different ways of bounding this thing. And one that I find particularly beautiful is a mutual information theoretic one. So here, you upper bound the generalization error by something that depends, wrong button, by something that depends on the training data size. So M is the number of samples that you saw, and the more you see, the better you're bound. And it depends on the mutual information between the training data that you saw and the hypothesis or the parameters that you end up with. Okay? So the reason why I like this is because it has a nice intuitive interpretation. So this means if the thing that you learned is hyper-specific to the training data set that you saw, it's probably not going to generalize well to stuff that you haven't seen yet. So what you want is you want to be able to learn something, but not about the specific training data set. So this is an intuition in classical machine learning. And what we were asking ourselves in this project are two things. So the first question is, if we, remember my cartoon, make some parts of the picture quantum, what does generalization even mean? And I'll A, try to convince you that it's not trivial, And B, I'll propose a definition of generalization in the quantum case. And then the next question is, can we bound the generalization error that you're making? And here, the natural idea is, well, we know what quantum counterparts of information theoretic quantities are. So can we prove bounds that are similar to what I just showed you classically and have quantum information theoretic quantities play the role of the mutual information that we just saw? So my plan for today is to first do a super short review of the classical framework, then tell you about the quantum framework that we propose and about the bounds that we prove. And then I'll just highlight some applications of our bounds. And in this section, I will then essentially also hope for your support because we're still looking for more applications. Okay, but first of all, what's the classical framework? So now I'll go a bit more into detail of what's behind this motivation that I showed you. So I will call these things true and empirical risk. People give them different names like training error and testing error, but I prefer this one. So the scenario that I imagine is that your training data is a set of m IID random variables. So they're independent and identically distributed from some probability measure that describes the training data, and I'm going to denote the IID as like p to the m. You might also want to write this as like p to the tensor m or something. And you should think of each z as consisting of like an input and an output, right? So this would be like the input and the label. The next ingredient we need is a classical learning algorithm. And I'm going to think of learning algorithms that have some kind of randomization built in. For example, this could be because your gradient descent is a stochastic gradient descent. In principle, you could also describe deterministic learners this way, but for today, it makes more sense to think of randomized learners. So if you do this, then a learning algorithm is described by a conditional probability distribution that tells you if you see a training data set S, what's the probability of outputting a hypothesis W? Notice that I'm implicitly assuming things are discretized here. This is not super crucial, but it makes many things easier. So I'm not thinking of a probability density, I'm really thinking of a probability distribution. And this then, together with the training data distribution, induces a joint probability distribution over the data and the hypothesis. And notice that this depends on the learner because this conditional distribution depends on the learner. Okay, and then here really, as I said, the thing to keep in mind is that your learning algorithm describes the conditional parameter distribution that you get from stochastic gradient descent. And then finally, we need a way of evaluating performance. This is typically done via so-called loss functions. So a loss function is a map that takes as input a hypothesis and a data point and assigns to it some usually positive value. So a large positive value is bad. You want a small positive value. One of these standard examples would be to take your L of a hypothesis and a data point, again, data point being input and label, to be the difference between the hypothesis evaluated at that point and the true label, and you square it. Of course, if you have like 0, 1 labels, this is either 0 or 1, so you could write it in a different way, but if you have a continuous space, then you might want to write it like this. So this is the ingredients of the classical setup, and then we need two notions, namely these two ingredients that I had in the generalization error before. So we need the expected empirical risk, which you should think of as the expected average loss that your hypothesis incurs on your training data. Okay, so this is the data that you see during training, and you ask, how well are you doing on that? And then I'm taking an expectation value over both the data and the hypothesis. And the shorthand notation for this is something like this. I'm using R for risk, and the hat is for empirical. So this is the training performance, and the testing performance, I call it true risk. You get that by taking a new sample that you haven't seen, so it's independent from what you trained on, and you look at the average loss. And one thing that's an important insight, even though it's a very easy one, but still an important insight in classical learning theory, is that you can write this like an expected empirical risk with the subtle change that your distribution is no longer a joint distribution over data and hypothesis, but you work with independent copies of data and hypothesis. Okay, so this means that your testing error, your expected testing error, has the same functional form as your expected training error, but you decouple the random variables that describe your data and your hypothesis. And then the expected generalization error that I showed you before is just the difference of those two things. Okay. And now let me quote this result that I like so much by Aulin Zhu and Maxime Raginsky, who proved that if your loss function is kind of nice, mathematically it should be sub-Gaussian for every fixed hypothesis, then they proved this generalization error upper bound that I showed you before in terms of a mutual information. Okay, so this is a classical mutual information. I'm not going to formally define it, but it tells you how much information, in this case, does the hypothesis W contain about the training data S that you saw during training. This is a really great result. At least I like it a lot. And what it essentially tells you is that if you think about the expected empirical risk and the expected true risk as being kind of the same thing, only difference being whether the training and the hypothesis are correlated or decoupled random variables, it tells you that decoupling these two random variables comes at a cost that is controlled in terms of a mutual information. So this is how I view this classical generalization. Okay, now I've been talking about classical stuff for a while. Probably I should start talking about quantum stuff. And here I first have to tell you how we propose to model quantum learning. And our goal here is to describe a scenario where you're learning from data that is part classical and part quantum. So we do this as follows. We have a training data system, which has these classical parts Zi, and then an associated quantum state. And what I mean by this is that you get this thing classically, but you only get a copy of the state, so not a classical description. And then you have multiple of these samples. But these states might be subsystems of some larger system. So they might be part of an entangled global system, which I view as the test system. And then you feed the training system into a learning algorithm. And a learning algorithm essentially will measure that thing, have some classical and quantum processing, and then they will end up with a classical hypothesis as before, but it could also retain a quantum system, so some quantum state that contains information that is then used for a prediction. And if you want to evaluate the performance of a learner, you have to keep around the test system and then perform some loss measurement that combines the information from these hypotheses and the test system. So in fact, the picture I show here is what we think of as the empirical risk, because here the training and the test system are still correlated. In fact, they could be entangled because we modeled it like this. If you want to get a testing error or a true risk, you have to cut the correlation, right? So you have to cut the correlation between the quantum systems. And in fact, you also have to cut the correlation between the random variables, but I was too lazy to draw that here. So in a few more formulas, our model is that the data is a classical quantum state. So it's some kind of average with a classical system describing a training data set tensorized with the corresponding states. This state lives in some data space. And then a quantum learner has some factorization of this data space into test and training data, can be described by some measurements performed on the training data space, followed by quantum channels that map the training space to a hypothesis space. And then if you look at what the learner does on the state, is it leads to, as before, as in the classical case, a joint distribution over classical data and classical hypothesis. But there's also a quantum system around. So it leads to a classical quantum output state, which is this sigma A that, oh, I'm sorry, this is not the right expectation value. This should be an expectation value with the joint distribution, my mistake. Where now, here the sigma A is a state that has both a hypothesis in it, but it also still carries the information from the test system because we haven't decoupled. Okay, and then if you now want to define risks in this way, we take inspiration from the classical case. So that means we don't have loss functions for quantum, so we have loss observables. But we define the expected empirical risk as the expression where everything remains correlated. So the classical random variables are still correlated from some joint distribution. And also the quantum state that has a hypothesis and the test subsystem is still a potentially correlated or even entangled state. Whereas to get an expected true risk, we're cutting the correlations. And we're cutting both. So we're cutting the classical correlation, meaning that we're dealing with independent copies of the random variables. And we're cutting the correlations in the quantum state. And in fact, we're doing a little bit more. So this is just the reduced density matrix of this state. This is not necessarily the reduced density matrix of this state. So this is the test system in the beginning of the procedure, before the learner started messing it up. I don't have time to go into detail why we think this is the right definition, essentially because it reproduces the right notions. But if you have these definitions of expected empirical and true risk, you can define a generalization error as the difference between the two. So let me emphasize again that the difference to the classical case is that now you have to decouple two things at the same time. So what we now have to do is we have to prove generalization bounds that show how these two decoupling procedures can be controlled in terms of information theoretic quantities. And what we prove is a quantum analog of the result by Zhu and Rabinsky. So what we show is that under a sub-Gaussianity assumption, which I'm not going to write down in detail, but it's like the quantum counterpart of the classical loss functions being sub-Gaussian. Then we can upper bound the generalization error, this quantum generalization error that I just introduced, by the following beast. So let's take this one at a time. There's an easy term, which we already know. So this is the classical term, which reappears here. It's a mutual information between classical random variables. The other two terms are genuinely quantum. So the first term here is a truly quantum mutual information, asking how much information is there between test and hypothesis system in these quantum states that we got from the learner. And the second term has what's called a Holevo information. So this asks, we have these kind of post-measurement states here, which and we're asking how much information do these post-measurement states contain about the hypotheses? So this is roughly what the Holevo information measures. The proof sketch is, there's a powerful tool called Petz's characterization of relative entropy. It's a variational formula. And there is an inequality called Golden-Thompson inequality. If you combine both, you can lower bound a relative entropy in terms of this expression here that has what we think of as a true risk, as a training error, and this log of the trace of a product state with an exponential. If you center the exponent and use what sub-Gaussianity means, you can simplify this a little bit. And now you have a lower bound on the relative entropy that actually looks like a difference between a training risk and a true risk, minus something else. Now you do some optimization and rearrange, and you're going to see that you get an upper bound that has a square root of a relative entropy in there. And if you know your entropies, you know that relative entropies will quite nicely lead to mutual information. It's not as straightforward because, as I said, this is not just the tensor product of the marginals. So then you have to work out what the expectations do. And there's a little bit of extra work that I'm going to skip for time reasons. So to highlight what we're doing is, now that we have both a classical and a quantum system, there's kind of two things that we could decouple. So we could decouple classically and we could decouple quantumly. So this means that whereas before we just had a table with one row, we now have a table with four boxes. And we want to get from the upper left corner to the lower right corner. There's two ways of doing this, but we decided to do this step. So we first quantumly decouple. And this is what leads in our proof to the quantum terms. So this gives us a quantum mutual information and a Holevo information. And then we do the classical decoupling that's already there in the classical literature that gives us the classical mutual information. And in fact, you need these terms. So you can show examples or reinterpret the classical case in different ways, showing that the terms are in fact necessary. Okay. As I promised, I'm going to argue, or at least claim, that there are some applications of this. Otherwise, it wouldn't be much use. So without going into too much detail, let me say that the first application we have is based on these results. We can give an information theoretic tightening of the pretty good state tomography result that Aronson had in his seminal 2007 paper. So what I mean by this is we can recover the result that Scott had, at least on average, but potentially, depending on your learning algorithm, our result is tighter because it depends on a mutual information, and to get Scott's result, you kind of brute force upper bound that mutual information. The second thing we can do is we can prove sample complexity bounds for learning measurements that you use for, say, state discrimination. And here again, we can prove bounds in terms of the complexity of these measurements, but you can also try to get at the more information theoretic quantity directly. Okay, and then finally, we can prove generalization guarantees from quantum differential privacy. So differential privacy is kind of popular in classical machine learning and has recently received some attention in the quantum world. And what we can say is that an algorithm that enjoys privacy will also generalize well. We have some more applications in our paper, but in fact, I'd say that we're still missing a killer application. So we proposed this framework, and we showcased that this framework encapsulates some results and even proves some new results. So this first result is recovering something that already exists. The second result, I don't think has been explicitly stated in the literature. And the third result, to the best of my knowledge, is really new. But I think there's more room to apply this framework. So to conclude, the guiding questions for my talk were, what does generalization even mean if we allow classical and quantum data and hypothesis? And also, can quantum information theory help us bound a quantum generalization error? So I hope that my pictures at least gave you an idea of what I mean by generalization, and I hope that the theorem gave you an idea of how we answer question 2. So we showed this kind of framework for generalizing in learning problems from CQ data. And while this already covers lots of things, it doesn't yet cover all learning problems that you might think of. So for example, it doesn't cover classical shadows or shadow tomography. And extending the framework to include those is an open question from our work. Second, I showed you some quantum information theoretic generalization bounds. And here, there's been loads of classical improvements to these bounds. And it's actually not obvious how to quantize them because some of them rely on conditioning, for example. So I think this would also be interesting. And then finally, we gave several principal applications, some of them new. But I think there's lots of room for concrete or improved bounds under extra assumptions. All right, that's it. Thank you so much for listening. And if you have any questions, go ahead.
Indeed, are there any questions? Yes.
Very simple one. So the classical bound, what are the applications?
Yeah. So the main reason why classical people care about these information theoretic generalization bounds is because most of the bounds we had before just ask, how complex is the space of all possible models that you could end up with after training? And this is often overkill. So this leads to bounds that are in practice useless. For example, bounds based on VC dimension. These information theoretic generalization bounds can be tighter. So for example, people have used the information theoretic approach to explicitly study generalization behavior for algorithms that train based on stochastic gradient descent. There are also analyses that relate training algorithms that regularize with information theoretic quantities to Gibbs algorithms. So there's quite a lot of improvements of existing bounds, but even in the classical literature, I think they're somewhat lacking a killer application. So by now, they know how to reprove almost every generalization bound you can ask them about with information theoretic arguments. And they've got some numerical experiments highlighting that they are really better, but I think they're not yet the end of the story, as at least my current understanding of the classical literature.
So even in the classical case, can I understand? Sorry, is this bound kind of relative in the sense that, you know, if I have two models and like one has like a smaller upper bound than other, then I can somehow say that it's better in that sense. Is that correct or not? Because if that is the case, then the bound would be really useful. If it's not, then
they're not tied upper bounds. So just because one bound is smaller than the other does not mean that that model is strictly better. Mhm. Yeah. Yeah. Thank you for the question. So this is maybe something I didn't make clear enough. So when I say CQ for our models, I don't mean that you need a classical part. In fact, okay, this is going to take ages. In fact, what I mean is that you can have a classical part, but this also applies for purely classical models. So, whoops. If you look at this picture here, you could just throw out the ZIs and you would have purely quantum data, purely quantum processing, and if you want, a classical or a quantum hypothesis. So for example, you can phrase average case versions of classical shadows or shadow tomography in our framework, and they would have only quantum data. It's just that our framework doesn't quite reproduce the strongest guarantees we have yet. So that's the weakness. But yeah, the goal was exactly to be able to say something about purely quantum data as well. Yeah. Yeah, I think you can think about it both ways. So I'm saying the QQ is like a special case of ours because ours is like CQ to CQ and you can just throw away the Cs. But you're also right that in a sense, the QQ is a generalization of what we're doing.
Great. Then let's take the rest of the discussion offline and we see each other in like 3 minutes. And let's thank Matthias again.
Yeah, try. Okay.
Okay, then let's get ready for the last talk of the session. Everybody settle down quickly. Right, so the last talk of today's afternoon session is on learning quantum states of continuous variable systems, and we have the pleasure to hear from Francesco Mele about this.
Thank you very much. This work was possible thanks to the huge effort of this wonderful team of people: Antonio Annamele, my twin brother, Lennart Bittel, Jens Eisert, Vittorio Giovannetti, Ludovico Lami, Lorenzo Leone, and Salvatore Oliviero. Most of them are also here in this room. Okay, this talk is based on two main topics: the topic of quantum learning theory and the topic of continuous variable systems. Quantum learning theory has been extensively developed for finite-dimensional systems, but this is not the case for infinite-dimensional systems, like continuous variable systems. The central problem in quantum learning theory is quantum state tomography. That means learning unknown quantum states. Despite many heuristic tomography methods available in the quantum optics literature, the literature lacks rigorous performance guarantees of tomography of continuous variable systems. In particular, a comprehensive analysis of the sample complexity has never been performed for continuous variable systems, for tomography of continuous variable systems. And in this work, we fill this gap. The outline of the talk is as follows. I start by giving an introduction to quantum state tomography, then talk about continuous variable systems, and then I will talk about our results on tomography of continuous variable systems. So, quantum state tomography means learning unknown quantum state. You can imagine that you have an experiment, and then when you run this experiment, the output is a quantum system initialized in an unknown quantum state row. And the goal of a tomography algorithm is to learn the state, basically to provide a good approximation of the state. Basically, the tomography algorithm takes in input many copies of the unknown state row and outputs a classical description of a quantum state rho tilde, such that it is a good approximation of the true unknown quantum state row. The output, so rho tilde, approximate rho. In which sense? Now we precisely define what does it mean that rho tilde is an approximation of rho. Basically, rho tilde has to be close, very close with to rho, with some meaningful notion of distance. And the most meaningful notion of distance to distinguish quantum states is the trace distance. This is due to the operational meaning due to the Euler-Wallström theorem. So what we are requiring is that the trace distance between rho tilde and the rho is very small, is epsilon close, is epsilon small. So basically, the trace distance between rho tilde and rho is less than epsilon. And here there is another observation to do. Basically, rho tilde, the output of the tomography algorithm, is a random variable. This is because the outcome of quantum measurement are inherently probabilistic. And so the condition that we have to require is that rho tilde is epsilon close to rho with high probability, with probability that is larger than 1 minus delta, where delta is a small parameter. Delta is called the failure probability, while epsilon is the trace distance error. Okay, and tomography algorithm is designed to learn state in some prior assumption set of states, called denoted as S. In summary, the problem of tomography is as follows. Given n copies of the known state rho in the prior assumption class set, the goal is to output a classical description of state rho tilde such that is epsilon close to rho with high probability. In order to measure the performance of the problem of tomography, one introduces the concept of sample complexity. The sample complexity is the minimum number of copies that allows one to achieve tomography. The sample complexity depends on the prior assumption set, on the trace distance error, and on the failure probability delta. And so it's just the minimum number of copies to achieve tomography. For example, if you don't have any prior additional information on your state, if you just know that your state is a qubit, then the sample complexity of tomography of qubit is given by this formula. From the rest of the talk, I will just forget about the dependence on the failure probability because it's always logarithmic like that. So from now on, just delete the dependence on delta. And the sample complexity is just d square over epsilon square. If you have the additional information that the unknown state is pure, then the sample complexity reduces to d over epsilon square. Okay, what is important here, and I want you to remember for the rest of the talk, is that the dependence with respect to the trace distance error here, it's always like 1 over epsilon square. This will be important later. And okay, moreover, for n qubit states, the dimension is 2 to the power of n, and so the sample complexity scales exponentially in the number of qubits. It scales exponentially in the system size. And when the sample complexity does not scale polynomially, we say that this task is inefficient. So tomography is inefficient. Okay, let's talk about continuous variable systems. We are basically talking about quantum optical systems. Here, the role of one qubit is played by the so-called one mode. One mode is basically one qubit with d equal to infinite. One mode is basically an infinite dimensional qubit. The Hilbert space of one mode is the span of ket 0, ket 1, ket d, and so on and so forth. These are called the Fock states. Ket 0 is the vacuum state, ket 1 is the single photon state, and ket d is the state with d photons. By definition, a continuous variable system is a system that consists in n modes. It is n qubits with d equal to infinite. Okay, now let's talk about our results. So, strictly speaking, without any additional prior assumption on your unknown state, tomography of continuous variable systems is impossible. This is just because the dimension is infinite and the sample complexity is infinite. However, for any practical purpose, you always have an additional prior information on the energy of your state. For example, you always know that the energy of the light source that you have in lab is upper bounded by the energy of the sun, or maybe by the energy budget that you have in the laboratory. So the crucial observation is that in lab, continuous variable systems have bounded energy. Okay, let's formalize this concept. We have the energy observable, also called the total photon number, defined as follows. It acts on the tensor product of n Fock states as this, by counting the total number of photons. And the assumption that we are requiring on the unknown state rho is that it satisfies an energy constraint. So the assumption is that the unknown state rho satisfies that the expectation value of the energy observable is upper bounded by a known parameter, E tot. This known parameter has to be understood as for example, the energy of the sun or the energy budget available in the laboratory. Okay, so since we are interested in the scaling with the system size, with the number of modes, and since the total energy is an extensive quantity, and we don't want implicit dependence on the number of modes, and we just redefine the total energy by putting n here, in order to don't have implicit dependence on the number of modes. And so now This is just a redefinition. It's not really important. Now E represents the energy per mode, and it is a known parameter. Okay, so our first main results regards the sample complexity of tomography of energy constrained states, pure states. We find this sample complexity, and it is given by this formula. So this number of copies of the state is not only sufficient, but also necessary to achieve tomography. And this result is quite informative because it tells us that the sample complexity does not only scale exponentially in the number of modes as in the finite dimensional setting, but it also exhibits this very bad scaling with the trace distance error, which while in the finite dimensional setting, the behavior with the trace distance error, it's just 1 over epsilon square. Here in continuous variable systems is 1 over epsilon to the 2n, which is very bad. And just to understand why it is bad, consider that if we want to halve the trace distance error, epsilon, if we want to decrease the trace distance error by a factor of 2, in the finite dimensional setting, you just need to increase your number of copies by a factor of 4, which is cheap. While in the continuous variable setting, you need to increase your number of copies by a factor 4 to the power of n, which is extremely inefficient, extremely expensive. This is why we say that continuous variable tomography is extremely inefficient because of this bad scaling with the trace distance error. Let's just make another example to understand this inefficiency. Let's consider first the qubit setting. So let's consider tomography, and let's consider that we run the experiment every 1 nanosecond. And let's say that we want to achieve trace distance error 0.1. Okay, let's consider tomography of 10 qubit states. It turns out that the total time required to achieve tomography is 0.1 millisecond, which is not so much. It is achievable. Okay, now let's consider the analogous problem in continuous variable systems. Let's consider the problem of tomography of 10 mode states with energy per mode upper bounded by 1. This is a fair comparison with 10 qubit states because energy per mode upper bounded by 1 means that on average you have at most 1 photon, and the other photons are suppressed. So basically, by applying our sample complexity formula, it turns out that the total time required to achieve continuous variable tomography has to be at least 3,000 years. That shows a huge separation with the qubit setting. Okay. So we have proved that tomography of continuous variable systems in general is extremely inefficient. And this can be regarded as a no-go result. Now, let's say a positive result. In many practical situations, you have the prior information that your state is Gaussian. Gaussian states are very common in lab and in nature. And here we can show that tomography of Gaussian states is efficient. And okay, now I just tell you the idea of this fact. Okay. I will not enter into the definition of Gaussian states. I will just tell you that a Gaussian state, as in classical probability theory, is uniquely identified by the so-called first moment and covariance matrix of the Gaussian state, of the state, as for Gaussian probability distributions, classical probability distributions. This is also true for quantum Gaussian states. Okay. This is the only fact that we need, that a Gaussian state rho is uniquely identified by its first moment and its covariance matrix. Basically, if you specify the first moment, the covariance matrix of a Gaussian state, you also specify the state. And what is important is that these quantities, these moments, can be efficiently measured via the so-called homodyne measurement. And so if you estimate the moments, you also provide an estimate of the state. because of this one-to-one correspondence. And now a natural question arises. In practice, you can only have epsilon approximation of the moments. And however, we are interested in the trace distance error on the state, because the trace distance is the most meaningful distance to distinguish quantum states due to the Olevo-Elstrom theorem. So the fundamental question that arises here that we propose is that if we estimate the moments of a non-Gaussian state with a certain precision epsilon, how this error epsilon propagates into the trace distance, on the trace distance error on the state. This is crucial to analyze the sample complexity of tomography of Gaussian states. And we answer this question by providing upper and lower bounds on the trace distance between two Gaussian states in terms of the norm distance of their moments. Okay, this is the upper bound, this is the lower bound, it's not really important. And we have that trace distance error is at least epsilon and at most square root of epsilon, where epsilon is the error on the moments. Okay, and Alexander Olevo got interested in this question, and a few weeks ago proved a new upper bound on the trace distance between Gaussian states that can outperform our upper bound in some regimes. And take a look to Olevo's new beautiful paper. Okay, by exploiting this new tool, we can perform a sample complexity analysis of tomography of Gaussian states and prove that the sample complexity is polynomial in n in the number of modes. And this proves that tomography of Gaussian states is efficient. Okay, to summarize, we have proved that tomography of arbitrarily non-Gaussian states is extremely inefficient. On the opposite side, we have proved that tomography of Gaussian states is efficient. The last part of our work, so a natural question arises. What is the trade-off between the efficiency in tomography and the degree of non-Gaussianity? The last part of our work studied this trade-off. And we studied this trade-off between the efficiency of tomography and non-Gaussianity by studying tomography of T-doped Gaussian states. T-doped Gaussian states are states that can be produced by applying to the vacuum state Gaussian unitaries and at most T single mode non-Gaussian gates. So if you start from the vacuum, you can apply Gaussian unity, then a single mode non-Gaussian gate, and so on and so forth for T times. Notice that for T equal to 0, the family of the set of T-doped Gaussian states coincides with the set of Gaussian states. Then the set of T-doped Gaussian states enlarges as T grows. And then it, when T is equal to infinity, it becomes the full set of states. So in this sense, by studying how the sample complexity behaves with respect to T, we can study how the efficiency of the tomography behaves in terms of the non-Gaussianity. And in order to study this, we introduce a theorem, a compression theorem. It says that if you apply a suitable non-Gaussian, suitable Gaussian unitary to a T-doped Gaussian state, you can compress all the non-Gaussianity in the first T modes, in the first two T modes. And this is a bosonic generalization of analogous results known in the fermionic and in the Clifford setting. And this shows an intriguing parallelism between the three theories of bosons, fermions, and Cliffords. Okay, with this compression theorem at hand, we can easily come up with a tomography algorithm for T-doped Gaussian states. I will not enter into detail of this algorithm because there is no time, but I would just go to the conclusion and say that if T is a constant, then tomography of T-doped Gaussian states is efficient. And the sample complexity, scales at most as n to the power of t. So when t is constant, the sample complexity scales polynomially in the number of modes, and so tomography of t-doped Gaussian states is efficient. So in conclusion, in our work, we provided the first investigation of tomography of continuous variable systems with rigorous performance guarantees with respect to the trace distance error. We find the sample complexity for energy-constrained pure states, and we showed the phenomenon of extreme inefficiency of continuous variable tomography due to this very bad scaling with the trace distance error. And then we showed a positive result that tomography of Gaussian states is efficient. And then we studied the trade-off between these two results. These are two limits results. We studied the trade-off between Gaussian states and arbitrary non-Gaussian states by studying, by deriving a result on the trade-off between efficiency in tomography and degree of non-Gaussianity, by studying the sample complexity of tomography of t-doped Gaussian states. And last, we introduced the technical tools of independent interest. For example, bounds on the trace distance between Gaussian states in terms of the norm distance of their moments. Okay, thank you for the attention.
Great. Are there any questions? Oh, a lot of them. Let's start here.
I have a very naive question, and apologies for my ignorance about continuous variable systems. But for discrete variable systems, if we don't look at the trace distance, but look at other measures of distance, which are kind of looser, then I think the bounds are much more favorable. It does not go exponentially in the system size. So could something similar be done for continuous variable systems as well?
Yeah, I would expect so. Yeah, but I think that performing an analysis with respect to the trace distance is what it makes sense, because it has an operational meaning.
What I mean is, if these quantities were vectors instead of matrices, we could look at the infinity norm. And in the infinity norm can be kind of found out, finding it is much more easier than finding, say, the 2 norm, which is more conventionally used. So other norms other distance metrics could also have physical meaning, but could still be easier to find. So any thoughts about that?
Okay, we don't have analyzed the other norms, just the trace distance.
Okay, thank you.
Thank you.
Hi, yeah, I have a question about the continuous or energy constrained states. I think you said that if the energy is constrained to be about like 1, then that's like you have 1 excitation. In that case, I would imagine that your tomography is kind of like you're doing qubit tomography. So then the complexity would scale as like something that the complexity of learning a qubit. But I think you mentioned that it scales as like 3000, which is very different. So do you think it should reduce? Like, is that a fair assumption to make, that in that limit that you should get something that's close to the qubit case? Or
when I say that the energy per mode is upper bounded by 1, I just say that the expectation value of the total photon number operator is upper bounded by 1. For example, if you take a coherent state as is a superposition of all the Fock states, but if the amplitude is sufficiently small, it has a mean photon number, mean energy that is upper bounded by 1. So it's not a qubit state, but the overlap with the high number Fock states, with the Fock states with a high photon number is suppressed. It's very small.
All right, thank you.
Welcome.
Okay, one question here.
So for Gaussian states, is the energy related to the mean and the variance in some way? And
Yes.
Because like classically, like what is the intuition for why Gaussian states can be efficiently learned, because like classically they maximize like the entropy for when the moment and the variances are fixed. So
Okay.
just a feeling.
Yeah, the intuition is that while when you do tomography of non-Gaussian states, you have an infinite amount of parameters defining the states, all the coefficients of all the Fock states. For Gaussian states, you have just to learn a polynomial number of parameters that are those that define the first moments and those that define the covariance matrix. So n parameters, 2n parameters for the first moment, and 4n square parameters for the covariance matrix. So the number of total parameters is a polynomial in the number of bonds. So this is the intuitive reason why you just need the poly n number of copies to learn a Gaussian state, because you have just to measure poly n observables basically. But the tricky part of our proof lies in how to propagate the error from the moments to the trace distance. Yes. The energy of a state is given basically by the trace of the covariance matrix plus basically the true norm of the first moment.
And maybe the last opportunity for a short question. Short? Very good.
Do you think that the dependency on epsilon will still remain if you consider shadow tomography instead of tomography?
Okay. Okay. Classical.
Shadow tomography, not necessarily classical shadow tomography.
I see. Okay, so I don't know the answer for. Okay, actually, classical shadow is also an algorithm for shadow tomography, and okay. So the answer is no. As long as the number of observables that you want to learn, it's fixed. The observables satisfy some suitable conditions. You have the same results that also in the finite dimensional setting. But if you want to use the classical shadow algorithm to perform tomography, then has to satisfy these fundamental limits on the sample complexity. Yes.
Great. Then let's not only take the opportunity to thank Francesco for his nice talk, but also for not yet, but also all the support people that have been that have made it possible to run so smoothly this afternoon session. Thank you.
Thank you.